Okay, I think we're going here. So we have the pendulum, simple pendulum. The main thing here is to show the vectors and the energy. We'll talk about the energy later. First we have the vectors, the main thing I want to show in this. So let me stop this and let's see what we've got. So here's our object. We have a rope, or actually something stronger than a rope, something like a metal rod, because we might want this to go way up here and a rope wouldn't work. A rope, of course, would just collapse. So this is a thin, massless, as we say in physics, thin metal rod that's supporting this thing. This vector represents the tension in that rod that's holding this mass in position along this circle as it moves. So we'll watch how this vector changes as the motion progresses. And this vector is gravity, of course, straight down, and it's constant. And this is the force along the direction of motion that's the resultant of these two guys. So let's let this move and just watch it for a few minutes and see what happens. Here we go. Just watch what that does. See how this gets a little bigger? A little bigger at this. This is the largest when it's straight up and down. Watch that one. See? And as it goes off to the side, it gets a little shorter. This one is always pointing back toward the center. So watch how this switches direction. It's always pointing back toward the center. And the gravity, of course, just stays straight down. So this force, the one along the direction of motion, is, of course, what causes the motion. And as long as it meets the conditions, here, let me stop this. As long as it meets the condition that this vector is always aimed, the force represented by this vector, is always aimed back toward the rest position, which we can show is, well, actually, because I have an initial angle here, let me bring this back to 0. Let me see if I can get that back to 0. Okay, that's going to be our rest position, right about there. Okay, there we go. So this is the equilibrium position, and for simple harmonic motion, we need a force that always directs the object back toward this position. So as we saw when this was running, we have to give it a little initial and let it run again. Watch what it does. It switches. It always points back toward here. So that meets the condition that we need for simple harmonic motion. That's one of the conditions. The other condition is that this force needs to be directly proportional to the displacement. Now here, the displacement is measured by this angle. All right, we don't measure the displacement as a distance along this arc. I mean, I guess we could, but we don't do that. We use this angle as our displacement variable. Now I've got this coded so that this vector is proportional to this angle. Now it turns out, you can see in the other video, that this just is not true for a real pendulum. This is an approximation that is actually only good. Let me see if I can bring this back down to where you can't even see the vector. For a small angle about like this, the other video will show this. This vector is so small you can't even see it, but it's still there. In fact, let's let it run. See, watch what it's going to do. Notice it moves a lot more slowly. We'll talk about that in a minute. Okay? Now that would be simple harmonic motion. This is correct because it's a small displacement angle. There's a mathematical reason why that works that way. It has to do with the approximating the sine of an angle with the angle itself in radians, which you can see on your calculator. If you go into radian mode, graph sine of x, and then graph as y1, and y2 is just x, y2 equals x, and graph that and look at the region right close to the origin, and you'll see that the curves overlap each other. So sine of x, if x is small in radians, nearly equals x in radians. So that approximation is used here to solve this, and you get a very simple solution. And this motion is valid, and we'll show that on the other sim. You'll be able to see that this works just fine like this. Now, what I've done in this particular program, because I really want you to see these vectors, I went ahead and kept this proportional to this angle for any angle. And I'm saying that that's not strictly true in the real world. Well, it's not even close to being true. The other simulation really shows that. We'll see in the other video, we can see that. Okay, so let's just let this go. Just watch what these vectors do. Whoops, here we go. And then we'll come over here and talk about energy in a second. Okay, so just see how this vector, it gets bigger in proportion to this angle. All right, so we have two conditions to make this simple harmonic motion. We need this force to always come back to the center, which it does. And we need for this, the magnitude of this force to be directly proportional to whatever the displacement variable is. In this case, it's the angle. Now again, this has been coded this way just so you can see this, but it's not legitimate. It doesn't actually work this way. We'll see how it really works in the other simulation. All right, and let me see if I can get this guy here. Let me stop this. Let me see if I can get this scale back down to where we can see what's going on over here. All right, these are our energy curves. Now, one of these is potential energy and one of is kinetic. Now, which is which? Let's think about it. When this thing is at an extreme, here, let's let it move. Let's get it going again. Okay. When it's at an extreme here, at each end, it stops. So its kinetic energy would be 0 at the max angle. So for 0 is down here. So that says that this curve up here, this parabola that's a concave down, is the kinetic energy. It also says the kinetic energy is a max at 0, which means when this thing crosses through the 0 point here, it's going the fastest. Since kinetic energy is 1/2 mv squared, the mass doesn't change. The only thing is changing is the velocity. So as it crosses the 0 point, which is the equivalent of right here, that's the max kinetic energy. All right, and then the potential is just sort of the inverse of that. This is concave up. Now let's think about the potential. Let me stop this. Put it out over here, doesn't matter. Okay, now the potential energy is just the height of this center of mass of this thing, which is right about there, above the 0 position, which is right about here. This difference in height, right about from here to here, mgh, potential energy, same way it always is. Okay, so the potential energy is it min or max at the center point? Well, let's move it down to the center. See if we can get it down there. It's going to move it. I can move it faster than that. Right about like that. Close enough. Okay. The potential energy max here or min here? Well, if there's no displacement from the lowest position, gravitational position, that's got to be 0. So that's this guy right down here. See this little blob down here? And this curve is concave up. That's the potential energy curve. The potential energy increases as we go farther up. You can't see it here, but it's up at the top. All right, so let's just watch how that exchanges as we run this. Okay, and then just watch the little green blob. Potential energy, max, min, max, min, max, min. It's minimum potential energy at the center point, the equilibrium point, and maximum potential energy up at the extremes when it stops moving. And the kinetic energy is just the inverse of that. Now you might figure from that that the sum of those would be the same. It would be a constant. The sum of those would be a constant, and that's true. Because what happens is when you start this system, well, let's put it this way. If we put it back down to here, let me put time back to 0 and put this angle back to 0. If I can get it back to 0. Okay. Right about there. Okay. Now the system has no energy in it at the moment. It's just sitting here. It's not doing anything. But when you move this, when you pick this thing up and thumb and finger and move it, give it an initial angle, move it up here, you are doing work. You are displacing this thing against gravity up to this height above where it was. Okay, and that doesn't seem like you're doing anything because usually this is very light, and plus the tension is holding most of the weight anyway, right? This vector is holding most of that. So when you move this, you're not really doing a whole lot of work, but you are doing some work and you're putting energy into the system. Okay, now that's potential energy that's in the system. As long as you just release this and don't throw it, that's all the energy there is. And so as this thing moves, it exchanges back and forth between kinetic and potential on these curves, as we saw. Here, let's let it run. You can see it. Okay? These guys just exchange back and forth such that if you add these together, you get a constant. Right? The total energy of the system is conserved. This is called mechanical energy. Potential energy and kinetic energy together are called mechanical energy. And that's all there is. What you put in it when you gave it that initial displacement. And the other sim will be able to see what happens if you give it a throw. If you actually input some kinetic energy into the system. That has certain effects that we'll see later. But for here, we're going to just let go of it. So our total energy is going to be up here when you add these two guys. It's going to be, well, actually, it's right here, right? Because if this is 0, this is this, that's it. In fact, let me think about that. Let me go back, set this back here. So the total energy in the system that we've put in is right here. So it is what is this value? 1.5. Energy would be joules right here. And then as that comes down, this guy comes up. They're equal at this particular point. When this guy is maximized, the kinetic is maximized, the potential is minimized. Okay? So let's just watch this again for a second. See how this looks. All right? So if you add these two together, you get a constant. And that constant is the energy that you put in the system when you initially displace this thing. Okay? So that's this one, just to show you how these vectors behave. Let me make this a little more extreme so you can watch this vector that goes to the tension. Let's go up here where there's a real, see, look at this. Look how little, don't worry about this curve. Look how little tension there is now when this thing is up at this steep an angle. Now watch this guy especially when this runs. Watch what happens to that. Whoa, see, it gets real big at the bottom and real small as it goes up on the sides. All right? Pretty cool. All right, so that's it for this one. Now we're going to move on to the next video.